Hello everyone! In this lecture, we will take a broader look at a very important browser security concept called the same origin policy. And we will also cover related topics like cross-origin resource sharing and cross-site leaks. But first, let's start by looking at the web security threat model. So what is the threat model under which web technology should function securely? So the core security guarantee of the web is that users can safely visit arbitrary websites and execute scripts provided by those websites. As you see, in this threat model, the website is the attacker, and the attacker must not be able to, first, compromise our browser or computer, and second, must not be able to see or interfere with our interaction with other websites. For instance, if we have Gmail opened in one browser tab, we don't want a malicious website opened in another tab to read our emails, right? And this is where our browsers apply a set of rules called the same origin policy, which is the central topic of this lecture. The same origin policy is a fundamental security mechanism that prevents one website running inside the user's browser from attacking another. So what it means in practice is that it should be safe for us to browse two different websites in parallel, no matter whether they are opened in two different browser windows or browser tabs, or even if one website embeds another website inside it using iframes. So this same origin policy enforces isolation between scripts running on different websites, such that these scripts could not interact with websites belonging to another origin. So even if this website A embeds website B in its web page, the scripts running inside website A security context should not be able to read out what website B here is showing to the user. In other words, the same origin policy enforces that scripts running in one origin cannot access resources of another origin. If our browsers did not enforce such a policy, then a script running on a malicious website A could simply load a website B in an iframe and read out all sensitive data that website B is showing to a user and perform any action inside website B on behalf of that user. Now, a website origin here is defined as a triple consisting of scheme, host, and port. This means that websites running on different hosts, even if they belong to the same root domain, will be considered different origins and therefore will be isolated from each other. So as you see, the same origin policy is much stricter than the same site policy used for sharing cookies, because the same site policy includes the root domain with all its subdomains. Now, what is important to understand here is that the same origin policy only ensures that cross-origin reads are forbidden, while cross-origin embedding is still allowed by the policy. This means that a malicious website can still embed an image or an iframe in its website. However, the same origin policy enforces that the malicious website will not be able to access the data contained in the embedded image or the DOM of the embedded iframe. Unfortunately, as you will see later in this lecture, this type of cross-origin embedding does not work as intended and in practice can be abused by an attacker to interfere with a website belonging to another origin. Anyhow, at this point you may come to the question, okay, so websites belonging to different origins cannot interfere with each other, but how could websites which belong to the same origin interfere with each other if they are, let's say, running in different iframes or browser windows? So let's look at different types of same origin access methods. Same origin access using frames works such that a website a.com embeds into itself an iframe loading this resource from the same a.com origin. Since this iframe is of the same origin, a.com has full access to the child frame, so it can access the document object model of the included web page and also modify it as needed. So in JavaScript, the window.frames object can be used to access frames embedded in the website. Now, the child frame also has full access to the parent website by accessing the window.parent object. So frames or iframes are the most basic same origin access method, although today modern websites should not use this method for same origin communication. Another same origin access method is by using opened windows. So a website, a.com, can use the window.open function to open another window to a web page at a.com origin, which will return a handle or a reference to that window. Now, in practice, depending on the browser settings, this window will most likely open in a new tab rather than in a separate browser window, but it is just a user interface nuance. The result is that a.com now has full access to the opened window via the obtained window handle. And also the opened window has full access to the opener window using the window.opener object. And just to note, a window handle can also be obtained for windows that are opened by clicking on an HTML link. But for that to work, the rel opener attribute has to be specified here, and we have to assign a name to the open window, which we can then specify here to obtain the window handle. Now, let's look at what happens if the loaded iframe or opened window does not belong to the same origin. So, in the case the cross-origin use of frames, a.com has no access to the child frame's DOM, and the child frame has no access to the DOM of the parent. This is expected as the same origin policy prevents documents from different origins from accessing each other. However, what is perhaps quite unexpected is that the parent and the child can still navigate each other. So the parent can redirect the child frame to another website, and also the child frame can redirect the parent window to another website. It is probably fine that the parent can redirect the child frame wherever it wishes. But why should a child frame from another origin be able to interfere with the parent window? So as you see, embedding frames from untrusted origins can also introduce some security issues for the embedder. Now, for the cross-origin use of opening windows, the result is very similar to frames. A.com has no access to the opened Windows DOM, and the opened window has no access to the DOM of the opener. However, here we have the same security issue as in the case of cross-origin frames, namely that the opener and the opened window can still navigate each other. The opener can redirect the opened window to another website or close the opened window at any time. And also the opened window can redirect the opener window to another website, but it cannot close the opener. Now, compared to the cross-origin frames, this security issue here is more severe, as it can be used in so-called tabnabbing attacks. This would be a type of phishing attack where a malicious website A.com opens a window to some legitimate website B.com, but after some delay redirects the B.com window to a phishing website C.com that mimics the appearance of B.com. And if the user fails to notice that the address bar of the window has suddenly changed, the user might enter passwords or other sensitive data on the phishing website. And this attack, of course, could also work in reverse, where the opened website performs an attack on the opener website. We will cover later in this lecture how to prevent these types of attacks. Note that domains belonging to the same site can relax the same origin policy by setting document.domain to a shared parent domain. So this would allow domains of the same site to communicate as if they were the same origin. Today, however, this method for subdomain communication is deprecated. It is not secure as it opens the website up for malicious access from any subdomain belonging to the same root. And it is also quite limited as it only works with subdomains and not completely separate domains. So it is considered legacy only and is being phased out by modern browsers. The postMessage API provides a better and safer method for cross-origin communication. Here is how it works. The sender calls postMessage to send an arbitrary message to the origin to which the window or iframe belongs. Here is an example where we are sending the message hello to the origin embedded in this iframe. From a security perspective, it is important to specify the target origin here in the second parameter to make sure that the message is transmitted to the intended origin, as there is no guarantee that when sending the message, the embedded iframe still points to b.com, as a redirect to another website could have taken place in the meantime. If the target origin specified here does not match the actual origin of the iframe, then the post message will fail with an error saying that the target origin does not match the recipient Windows origin and the data leak will be prevented. So the target origin should not be set to wildcard, as this would send the message to whichever origin is loaded in the iframe. To receive messages, the receiver listens for the message event. So here, the embedded page would add an event listener for message events, and whenever a message is received, it would log to the console the origin that sent the message and the data. And this is how it would look in this case. Note that the data here can be any JavaScript object, not just strings. From the security perspective, here it is super important to validate the origin from which the message is received, to make sure that the data is received from an expected trusted origin. If this check is not implemented and the website uses the received data to perform security critical actions, then it can lead to serious security vulnerabilities, as was the case recently with the Microsoft Bing website, which did not verify the origin of received messages. The result was that it was possible for a malicious website to open the Bing website and obtain its window handle, and using postMessage send a malicious JavaScript payload, which was then executed by the website. Recently, a similar vulnerability was also found in the Zoho website, and Facebook has also had a similar flaw. Anyhow, so this method works for both iframes and windows, and data can be sent in both directions. This cross-origin communication method does not involve sending network requests. The data here is transmitted by making it available to different JavaScript security contexts. Another cross-origin access method that involves sending network requests is using the JavaScript's fetch API. First, let's discuss it in the context of same origin access. So, using the fetch method, we can send very advanced HTTP requests to websites on the same origin. Here is an example of such a request. With fetch, we can specify pretty much any HTTP method here. We are not limited to just get and post. Then, we can specify any request header here, except for forbidden headers like user agent cookies and other headers that are reserved to be set by the browser. We can also set an arbitrary content type header and request body. For example, here we are posting some JSON data to the server and specifying the appropriate content type value. And most importantly, we can instruct fetch to include credentials, such as cookies, by specifying credentials include here. We can also spoof the refer header, but only to same origin URLs. So this is not really spoofing. And when the response is received, we can inspect it, including the HTTP status and return headers. In this example here, we are converting the response object to text and then turning it into a string and logging its value to the console. To summarize, this is a very powerful way for JavaScript to access and process resources from the same origin without needing to open new windows or use iframes. Now, what is important to know is that the fetch API can also be used to perform some limited cross-origin requests, but only very limited ones. Here is an example of such a request. So for cross-origin requests, only so-called simple requests are allowed. A simple request means that the request method must be either get, post, or head, and only a limited set of headers can be included. Accept, accept language, content language, and content type. But only a limited set of values can be specified for the content type header. These are form URL encoded, form data, and text plain, meaning that we can make cross-origin post requests to submit HTML form data or plain text. If we specify credentials include here, then cookies will be included and will also be processed accepted by the browser if they are set in the response. Now, the most important limitation here is that such a cross-site request will be sent to the server, but the response returned by the server will not be made available to JavaScript. And that is a same origin policy restriction. So we can use this method only to send simple and blind cross-origin requests, as we will not be able to read the response that is returned from the other origin. And if we think about it, this method is equivalent to cross-origin HTML form submission. We can submit a form to another website, but the browser is redirected there and the original website does not get to read the response. And that's why Fetch supports this limited cross-origin capability to provide the same kind of functionality that can be achieved using cross-origin HTML form submission. Alright, but at this point you may realize that there might be use cases where reading cross-origin responses would be useful. For example, if we want other websites to access resources hosted on our website. And this is where cross-origin resource sharing or CORS comes in. So the CORS method can be used to allow cross-origin reads. Here is an example. Let's say we have sourceorigin.com making a cross-origin fetch like we saw on the previous slide, but this time we specify mode CORS here. This tells the browser to return the response, but only if the target origin allows it. The target origin can allow it by returning specific headers in the HTTP response. So the response must include allow origin sourceorigin.com and allow credentials set to true. The allow credentials here is required because we ask to include credentials in the request. So if both of these headers are present in the response, the browser will return the response to JavaScript. Now, an important note here is that this creates security implications for targetorigin.com because sourceorigin.com could now force the user's browser to perform any actions that the logged-in user on the target origin could perform. So this allow credentials true header should only be set if the target origin fully trusts the source origin. For example, when both domains are owned by the same organization. More commonly, we would only allow credential-less requests to be made. By allowing credential-less resource sharing, we usually don't introduce security risk other than this allows third-party websites to fetch data from our website via the user's browser. For credential-less requests, it is enough to return allow origin set to wildcard to authorize any website to access the resource. But if we use credentials set to true, we must explicitly specify here the origin that is authorized to access the resource. That is because allowing any origin to access resources with the user's credentials is generally very dangerous. Now, if we need to authorize multiple origins, we can solve this by generating the allow origin header dynamically based on the request's origin header. The origin header is included in cross-origin requests and it contains the website from which the request was made. It is similar to the refer header, but it includes only the origin part. So we can check the request's origin against our allow list, and if it is authorized, we include it in the responses allow origin header. What is also important here is that we need to include the very origin header here. This tells the browser and any caching servers that the response varies depending on the origin header in the request. Without this, a cached response for one origin might be incorrectly returned for a request from another origin. Think about that. So, to summarize, this is how we can authorize cross-origin requests to access data on our website. However, this method only works for the so-called simple requests we talked about earlier. If you want to send cross-origin requests using custom methods and headers, the target origin will need to support a mechanism called preflighted requests. So, coarse preflighted requests are used for non-simple requests, and here is an example of such a request. This request is non-simple because it sets a non-standard header x ping other and a non-standard content type value text XML. Before the browser can send this kind of request, it first needs to check if the target origin allows it, and this is done using a preflight request. A preflight request is sent using the options method. The browser includes the origin header field with the origin from which the request comes and 2 additional headers. Request method set to post, indicating that the actual request will be sent using the post method, and request headers, which list the custom headers that will be used. At this point, the server can decide whether to allow the browser to make such a non-simple cross-origin request. If the server approves, it sends back a response like this one, allowing this origin, this method, and these headers. There's also the max age header telling the browser how long it can cache this preflight result. If the max age header is not returned, the browser should cache the approval for 5 seconds only. If the browser is satisfied with the preflight response, it will send the actual request as requested by the fetch call, and the server will return the real response along with headers saying that this origin can access it and that caching should not be shared across origins. As you see, non-simple requests result in 2 coarse requests with a bit more complexity. Non-simple requests require preflight authorization because otherwise, even if the response is not accessible, simply sending such a cross-origin request could potentially harm target origins that are not expecting requests from other origins. Simple requests, on the other hand, don't require preflight authorization because any web application must be prepared to handle simple cross-origin requests initiated by random websites. Alright, so this is it about cross-origin resource sharing. Let's move on to another major topic of this lecture, which is cross-site leaks or access leaks. This is a very interesting and perhaps surprising phenomenon that we need to be aware of. As we discussed earlier, the same origin policy is designed to isolate scripts running in the security context of different websites. However, because of how the web and browsers work, there are still some very clever attacks that can allow a malicious website from one origin to infer some information about the user who is interacting with the site on a different origin. This happens because browsers expose various ways for websites to interact with each other. Just to note, another term for this kind of attack is a browser side channel attack. Alright, but what kind of information can actually be inferred through these type of attacks? The most basic thing a malicious website could determine is whether the user is logged in to a target website. And as you can imagine, even leaking that kind of basic information can already compromise the user's privacy. In most cases, figuring out whether the user is logged in would be the attacker's first step, but it doesn't stop there. In the next step, the attacker could try to verify whether the user's ID matches a specific value. So this would allow the attacker to de-anonymize or identify the user on the target website. Then, the attacker might try to determine whether the user has specific access rights on that website. And so on. As you will see from the different attack techniques, these attacks can be tailored to answer very specific questions about the logged-in user. So let's take a brief look at the most common attack techniques. Cross-site leaks through timing attacks are a very straightforward technique. The thing is that browsers make it quite easy to measure the time it takes to complete cross-origin requests. Consider the following script, which is executed in the user browser on an attacker's website. What it does is perform a cross-origin fetch request to the account page on the target website, and once the request completes, it displays how much time it took the browser to fetch the response. Let's say the attacker observes that it took 450 milliseconds to complete the request. Now, based on the timing, the attacker might try to infer whether the user is logged in. Typically, it would take longer for the server to generate a response for a logged-in user, because creating the account page for an authenticated session involves more computation than just returning a "please log in" message. So this kind of attack would first require the attacker to benchmark the target website to find out the average response time for a logged-in versus a logged-out user. And of course, the attack is more reliable on slower servers where the timing difference is more noticeable. And the same idea can be applied for extending the attack. Suppose the target website has a search form that allows users to search their medical records. Here too, timing can leak information. If the request finishes very quickly, it might mean that the search did not return any results, whereas if the response takes longer, the attacker might infer that many results were found and it took longer for the server to process them. Right? So I hope you got the idea behind these timing attacks. As you can see, even though they are quite basic, they can be surprisingly effective at leaking information about a logged-in user. Cross-site leaks through embedding content are another form of browser side channel attack. Let's take a look at a few examples. One interesting case is that the image element leaks the dimensions of a cross-origin image. For instance, an attacker could embed an image from a cross-origin website, and while the same origin policy prevents the attacker script from reading the contents of that image, the dimensions, the width and height, can still be read via JavaScript. And this can leak information if images of varying sizes are served to different users, such as logged in versus logged out. Now, you might be wondering, why on earth does the browser leak this kind of information to another origin? Well, the reason is that hiding the dimensions would not really help, because the layout of the attacker's page would change based on the embedded image's size, and there are plenty of other ways to detect such layout shifts. So that's considered a lost battle anyway. Then, error events can be used to leak the HTTP response status of an embedded resource. For example, if the onload event is triggered, we can learn that the success error was returned, while firing the onError handler would indicate that the response returned an error. This can leak information if the resource is only accessible to privileged or authenticated users. This method can also be used to check if the user's internet connection has access to the resource or it is firewalled. And just to note, using a script source is usually more reliable than using an image source. This is because some browsers may trigger an error also in case the request was successful, but the returned response is not a valid image. In contrast, the script element usually does not care about the file format issues in the response. Now, another cross-site leak is that frames and windows leak number of frames in the embedded or opened web page. For example, let's say we embed a cross-origin website in an iframe, then our script waits 3 seconds for the page to load, and then reads the number of frames in the embedded web page. Similarly, we can open a window to a cross-origin website, wait a few seconds, and inspect the number of frames in the web page. This can leak information if the number of frames varies based on user identity or privileges. Another iframe-based leak is that iframes can leak the presence of focusable HTML elements that have an ID attribute, meaning that a cross-origin website can determine whether a given ID is set anywhere on a target web page. So imagine that the target website for authenticated standard users includes a button to upgrade to a Pro account, where the button has the ID attribute set to Pro. The attacker-controlled website would embed the target website into an iframe and pass the ID attributes value pro as the URL fragment. Now, if an element with ID equal pro exists on the page, the browser will attempt to scroll to that element and the iframe will gain focus. And as a result, the attacker's website will lose focus, which will trigger the blur event. So if the attacker's website receives a blur event, the attacker knows that the iframe was focused, which means that the ID equals pro element does exist in the embedded page. So this can leak information if such elements are shown only to privileged users. And as you can see, this is quite a powerful access leak since most websites do show different content depending on the user's privileges. Another risk here is that short secrets such as tokens or flags placed in the ID attribute could be simply brute forced by trying this technique with many different values. Then, iframe also leaks whether the embedded website performs client-side redirects. If the embedded website performs a redirect, the frame will reload and we will see the load event fire, as it is fired every time the embedded page reloads. This can leak information if a redirect or reload is performed only for certain users, for example, privileged users. But what about server-side redirects? Well, there is a clever access leak for that too. Namely, using the browser's maximum redirect restriction, which leaks server-side redirects. The thing is that to prevent infinite redirect loops, browsers follow only 20 redirects, after what a network error is raised. And this behavior can be exploited to determine whether a cross-origin website redirects the user. So here is how the attack works. So here we create 90 dummy redirects and on the 20th step redirect to the target website. If the target website performs another redirect, we will exceed the limit and the network error will occur. Whereas if the request succeeds, it means that the target website did not perform a redirect. And this is how the browser's redirect chain would look in the case where the target website does perform a redirect. And again, this can leak information if a redirect is performed only for certain users, such as authenticated or privileged ones. Anyhow, so these were some of the most interesting techniques for exploiting cross-site leaks. But let's think now, what kind of countermeasures can we apply to defend against these type of attacks? So let's discuss how to prevent access leaks and strengthen our site against cross-origin attacks. First, we can apply framing restrictions. We can use content security policy directives to prevent other websites from embedding our site in an iframe. And we can sandbox any untrusted iframes we load ourselves. This helps defend against attacks where a cross-origin site loads our page in an iframe and vice versa where our website loads a potentially malicious page. Next, we can prevent other websites from accessing a window handle to our website. We do this using the cross-origin opener policy. This prevents attacks where a cross-origin site opens a new window to our site and obtains a reference to that window. Then, we can prevent cookies from being sent along with cross-site requests using what are called same-site cookies. We will cover this in more detail in the next lecture, but the key idea here is that most access leaks rely on the fact that browsers can send authenticated cross-site requests, meaning that session cookies are included in these requests. To block that behavior, our site can use same-site cookies, which will not be included in such cross-site requests. This helps in most cases, but there are limitations which we will discuss next time. And finally, we can block potentially malicious cross-origin requests by inspecting the segfetch request headers. This topic we will also cover in the next lecture. But for this lecture, let's focus on the first two defense mechanisms: framing restrictions and preventing access to window handles. Let's begin with restricting framing of our website. So using the content security policy header, we can enforce framing restrictions. For example, to prevent any website, including our own, from framing our content, we can return a content security policy header with frame ancestors set to none. If any website tries to load such a resource in an iframe, the browser will refuse to display the returned response in the iframe. So this effectively blocks any kind of attack that relies on embedding our site in an iframe. In fact, there are many more attacks that can be launched against websites that allow themselves to be loaded in iframes. We will explore those attacks in later lectures, but for now, just know that the best practice is to prevent other websites from framing ours altogether. Now, if we do need to allow framing in some cases, we can set a more relaxed policy by using a framing allow list. So we can use self to allow same origin framing, and here add specific trusted origins that are allowed to embed our content. Note that there is also the older Xframe options header, which provides similar functionality, but it is now considered obsolete and content security policy should be preferred. Still, you may occasionally see this header being used by some websites. Now, there are certain attacks that a malicious website can carry out when our website loads it inside an iframe. Therefore, we must also restrict the websites that we load into iframes. Here are some of examples of attacks a malicious iframed website can launch against our website. First, it can track visitors of our website. The malicious website can set cookies and identify unique visitors to our website. We will talk more about tracking risks in a separate lecture. Then, as we discussed before, the loaded website can count iframes on our web page, which can leak information if different users see different number of frames. Then, the iframe website can also redirect our website, the parent frame, to another website. This is not only annoying, but it can also be abused in phishing attacks where the redirect leads to a website that mimics our website's appearance. And it can also open new windows, launch pop-up dialogues, and trigger API features like playing audio, and so on. To summarize, the iframe website can do a lot to disrupt visitors of our website. To prevent most of these attacks, we can use the sandbox attribute here when embedding a website. By default, sandbox applies many restrictions unless specific allow parameters are added. Let's go over the most important restrictions that sandboxing provides. By default, it blocks JavaScript and other script execution unless execution is explicitly allowed by specifying the allow scripts parameter. So this blocks any JavaScript-based attacks. Then it also blocks access to the website's own origin, meaning that the iframe website cannot access its cookies, make same origin requests, and so on. So this should prevent cookie-based tracking of our visitors. Then it blocks attempts to redirect the parent frame, the website's window, although this attack only matters if JavaScript execution is allowed in the first place. Similarly, it blocks opening new windows or tabs and prevents alert dialogues from triggering. There are more restrictions that sandboxing applies, but these here are the key ones to mention. Now, the best practice is to never load untrusted cross-origin content in iframes, but if we have to, we should apply the principle of least privilege, sandboxing the frame, and only allow those exceptions that are actually required for the iframe's functionality. Then, the cross-origin opener policy is an HTTP response header that prevents other websites from getting a window handle to our website. So we can set the cross-origin opener policy header to same origin, which tells the browser that only our own origin can get references to windows belonging to our website. What this means in practice is that an opener from another origin will have no reference to the opened window. That means other origins can still use window.open to open a window to our website, but the window reference will be null. Also, the opened window will have no reference to the opener's window, so window.opener returns null. So this means that the opener and opened window cannot attack each other. And this prevents frame counting, cross-site leak, and window navigation attacks that we discussed earlier. Note that this applies also to windows opened by a website that sets the COOP header. So if our website sets this header, it won't get window handles to other sites opened from our website. This security header is also safe to apply by default, unless of course our website uses some unusual features that require window handles to other websites. Alright, so that's about preventing cross-origin framing and window opening attacks. Let's now discuss how browsers handle what is called mixed content. Mixed content occurs when a web page is loaded over a secure HTTPS connection, as you see here, but it loads sub-resources over an insecure HTTP connection. So here's an example where a web page loads a style sheet, image, iframe, and JavaScript over the insecure HTTP protocol. This is highly problematic because a network attacker could hijack these unencrypted requests and, for example, in the case of the script request, inject malicious JavaScript that could compromise the user browser session with the website. If an HSTS policy is in force for these resources, then this would not be much of an issue since these requests would be automatically upgraded to HTTPS. But what if HSTS is not in force? Historically, browsers would still load these insecure sub-resources, but would downgrade the page in the UI as not secure as if it had been loaded entirely over unencrypted HTTP. This, however, offers little protection since the attack could have already occurred. Today, to prevent such attacks, modern browsers will block any request that tries to load sub-resource over HTTP. When loading what is called passive content, like images, video, and audio, the browser will try to upgrade the request to HTTPS, while other types of requests will be blocked. This also applies to requests initiated by JavaScript. So, fetch calls to HTTP origins will also be blocked. Essentially, secure contexts today are not allowed to communicate with insecure contexts, while there is no such restriction in the other direction, meaning that insecure contexts can still send requests and load resources from secure ones. There are, however, a few exceptions to this restriction. First, the postMessage API can be used to send messages to insecure origins, but this requires opening a new window to the HTTP site because embedding insecure web pages in an iframe is blocked. Another case is top-level navigation, where secure contexts can still make HTTP requests to insecure contexts. In practice, this might involve client-side or server-side redirects or submitting HTML forms that send insecure post requests. However, when an HTML form is submitted, modern browsers will show a warning asking the user to confirm the submission of data to an insecure destination. Also, if a user clicks a download link that points to an insecure HTTP location, the browser will make the request, but if the response triggers a file download instead of a full page navigation, then the response will be rejected and the file download will be blocked as shown here. Again, this is to uphold the user's expectations that when interacting with an HTTPS site, all communication, including file downloads, occur over encrypted and authenticated channels. If the insecure download was initiated from an insecure website, it would not have been blocked. One more important exception is that local host origins are treated as secure contexts even when served over plain HTTP. This is because when we are connecting to a website running on our own machine, there is no data transmitted over the network, so there is no risk of interception. Also, setting up a valid TLS certificate for non-public hostname is tricky and requires interfering with operating system or browser certificate trustor. So this exception makes it much easier to develop web applications locally. Then there is a special opaque or null origin to mention. The null origin is used for originless resources, those for which the origin is undefined. Two resources that have an undefined origin are not considered same origin and are always treated as cross-origin. A good example here is resources that use the file scheme. The file scheme refers to files stored on the local file system. For security reasons, web pages accessed via the file scheme are given a null origin, which prevents them from accessing other files on the system. So, for example, a web page a.html will not be able to access the file b.txt. This means that the web page can load b.txt in an iframe, but it cannot read the contents of that frame, since b.txt is not considered same origin. If this restriction did not exist, a malicious website opened from our local file system could potentially upload all our personal files to some remote server. Thanks to this isolation, the damage a malicious file scheme web page can cause is quite limited. Similarly, resources that use the data scheme also have a null origin. The data scheme allows data to be embedded directly in a URL. For instance, here we use it to embed an image directly in an HTML element. This is convenient as it doesn't require loading an external resource. Now, we probably don't care much about the origin of an embedded image, but things get more interesting when the data URL is used to embed HTML that runs JavaScript. So in that case, the JavaScript runs in an isolated null origin. Sandbox iframes are also assigned the null origin, unless the allow same origin parameter is explicitly set. So even if iframe is loading content from, say, example.com, the content will be given a null origin and it will not be able to access example.com resources like cookies. Also, when a null origin makes a network request, the origin header in the request is set to null. In the context of cross-origin resource sharing, it is important not to trust requests coming from the null origin. This is because an attacker could use the data scheme or a sandboxed iframe to trick the user browser into sending cross-origin requests from a null origin. A notable example of this was a coarse misconfiguration on Facebook. Facebook mistakenly trusted the null origin, and this allowed a malicious website to make unauthorized requests to Facebook's API server on behalf of a logged-in user. As a result, attackers could access private messages, photos, and file attachments from Facebook chat. So, trusting the null origin turned out to be a crucial mistake even for Facebook. So that's a quick overview of the null origin. There are other contexts where it might appear, but these are the most common ones you are likely to encounter in practice. As the last topic of this lecture, let's look at the DNS rebinding attack. DNS rebinding is a clever and powerful technique that can be used to bypass the same origin policy, or more precisely, to trick a victim's browser into believing that web resources hosted on other servers belong to the attacker's web origin. The idea behind DNS rebinding is actually quite simple. Here's how it works. First, an attacker tricks the victim into opening the attacker's website, attacker.com, which runs malicious JavaScript in the security context of attacker.com. That JavaScript then makes a same origin fetch request back to attacker.com. Now, to establish a connection with attacker.com, the browser performs a DNS lookup to get the IP address, and this is where the DNS rebinding attack comes into play. The trick is that for this second DNS lookup, the attacker's DNS server returns, let's say, the IP address 127.0.0.1, which points to the loopback interface. The result is that this and future HTTP requests to attacker.com will be sent not to the attacker server, but to a web server running on the victim's own machine. And because the request still appears to be same origin to attacker.com, the malicious JavaScript can read the response and send it back to the attacker. This effectively turns the victim's browser into a proxy for accessing HTTP servers that are reachable only from the victim's network. So the IP address used here could have been any server that the attacker wants to access through the victim's browser. And this works because the IP address is not part of the same origin policy. And it should not be. We don't want to isolate origins based on IP addresses because it is common for a single website to be served by multiple IPs. At this point, however, you should recognize that there are two key preconditions for this attack to succeed. First, the target server must not validate the HTTP request's host header. For example, if the server performs a check like this, then the attack fails because the victim's browser will send this request with a host header of attacker.com. Most internet-facing servers, especially those hosting multiple websites, do validate the host header, as it is necessary to determine for which website the request is meant. But this often is not the case for small services running on local hosts or in private networks that don't expect to be accessed via any specific domain name. The second precondition is that no HTTPS must be used. If the server uses HTTPS, the TLS handshake will fail because the server will return to the victim's browser a certificate for domain other than attacker.com. So due to these two preconditions, this attack is unlikely to succeed against public websites. And even if it did, the attacker could just access these directly without routing requests through the victim's browser. Unless, of course, the attacker gains some benefit by sending requests through the victim's network. Now, in principle, even HTTPS websites could be vulnerable if the attacker controls any host listed in the website's TLS certificate. For instance, if the target website uses a wildcard certificate like you see here, then an attacker would need to compromise any subdomain to carry out the attack. But in practice, this attack is mainly used for using a victim's browser as a proxy for accessing HTTP servers in the victim's private network. It is especially effective for attacking routers and IoT devices, because those usually are not bound to any specific hostname, and also deploying HTTPS on IoT devices is a big challenge. To automate DNS rebinding attacks, a DNS rebinding attack framework called Singularity of Origin can be used. This is what the configuration interface looks like. It even provides a feature where the attacker can browse the target web server as if the attacker was using the victim's browser. For example, here is an attack where the attacker is browsing a Jenkins service running on the victim's loopback interface. Of course, this only works as long as the victim keeps the attacker's website open in their browser, so the attacker might need to apply some social engineering to keep the victim engaged. Anyhow, the takeaway is that web services that are running in private or seemingly protected environments should still protect themselves by implementing basic authentication and by validating the host header. This validation should be done either by the web server or the application itself. But with that, we wrap up the lecture.